Hello, this is a quick video to recap how you would calculate enthalpy change of formation using bond dissociation enthalpies. So I've got one example question here, which would be where you're set the challenge of calculating the enthalpy change of formation of HCl, and you are given the following values. So there's for the hydrogen, the chlorine, and the hydrogen to chlorine bond. If you haven't already attempted this question, please pause the video and do so now using those values. Okay, so the principle that we're going to use is from Hess's law, whereby if you go from one set of reactants to one set of products with all the conditions being the same, the overall enthalpy change will be the same. So simply, if I say that this is route A will equal step B plus step C. So route 1, direct route, and then I guess you could combine B and C to say route 2, this indirect route. So route A will equal route B plus C. Now, key thing for us here, however, bond dissociation enthalpies are always endothermic. The bond dissociation enthalpy is the enthalpy required to dissociate the bond. If we start off with reactants and we rip them apart to make atoms, which is what the bond dissociation enthalpy is showing, if we then put the atoms back together again to make the products, we're not using the bond dissociation energy, we're using the inverse of it, the negative. So the equation that I'm hoping that everybody has used is delta H is sigma, the sum of the bond enthalpies in the reactants, minus the sum of the bond enthalpies in the products. So it's a little subtle change here, because you are adding B and C, but here, this is the negative of the values. Okay, so if we would try and draw this out, you start off with hydrogen and chlorine. And what we have to do is we're going to go up, and we're going to break this bond, the HH bond, and we're going to break the Cl-Cl bond, and now we've got 4 atoms, gaseous atoms, completely separated. So the sum of the bonds here, it's hydrogen and chlorine. So down here I can write 436 plus 243, and what that's going to equal is 679. Now, we are then going to put these atoms together again in a different arrangement to make, careful, 2 HCl's. So down here I've got 2 times 432. The HCl bond is 432, but we will make 2 of them, one here and one there. So if we multiply 432 by 2, that will be 864. So at this point I can see that the exothermic step is coming further down than the endothermic step went up. This is plus 679, this is minus 864, which means that the overall reaction is going to be exothermic. More energy is released forming bonds than is required breaking bonds. Those are the phrases you need to use if you're asked to explain why the overall reaction is exothermic. So to reiterate, more energy released forming as opposed to required breaking. Key one where people drop marks is they say released breaking, but you have to point out it is required to break the bonds because it's an endothermic step. So we go up till we get to the atoms here, and then we come back down, and because more is released, the overall reaction is going to be exothermic. Quite often these questions have a generous mark scheme. You would get 1 mark for getting sigma, the sum of all the bond enthalpies that you had to overcome, and then another one for all of those that were being put back together again, and then the final mark, if you've laid it all out clearly, error carried forward will always be present, would be for this reaction the enthalpy change is negative 185 kilojoules per mole. And unfortunately, a lot of people will stop there. However, we wanted the enthalpy change of formation, which is the enthalpy change to form 1 mole of your compound. And if we have a look here, we've not formed 1 mole, but we formed 2 moles of HCl. So for here, we will need to divide by 2. And so for us, the enthalpy change of formation of hydrogen chloride is negative 92.5 kilojoules per mole. If you got that divide by 2 step, you get to feel pretty good about yourself right now. Otherwise, RTFQ.